Introduction. Today, physics teacher is going to perform an experiment in laboratory in front of students. He took a small balloon and put it in vacuum jar. Then he switches on the vacuum pump. Suddenly, the balloon starts to expand. After a while, he switches off the pump. Then, the balloon becomes in its original state. One student curiously asked, "Sir, will you please explain how this process works?" "Sure, Varun. This is an example of kinetic theory. When the vacuum is turned on, the pressure exerted on the balloon decreases, and the balloon can expand until the vacuum jar is completely filled. And when the air is allowed back in the jar, the pressure is re-established and the balloon returns to its original volume. This shows an indirect relationship between pressure and volume." So students, today we learn more about the kinetic theory. Objectives. At the end of this lesson, you will be able to define kinetic theory, explain molecular nature of matter, understand behavior of gases, define Boyle's law and Charles' law, know kinetic theory of an ideal gas, calculate pressure of an ideal gas, analyze kinetic interpretation of temperature, know Maxwell distribution function, define law of equipartition of energy, calculate specific heat capacity, define mean free path and Brownian motion. Definition. The kinetic theory was developed in the 19th century by Maxwell, Boltzmann and others. Kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms and molecules. This is possible as the interatomic forces, which are short-range forces that are important for solids and liquids, can be neglected for gases. Molecular nature of matter. All molecules of a gas are identical but differ from those of other gases. The molecules of a gas behave as perfect elastic spheres and are of very small size as compared to the separation between the molecules. All the molecules are always in random motion and they have velocities in all directions ranging from 0 to infinity. Molecules during their motion collide with each other and also collide with walls of the container. All these collisions are perfectly elastic. Molecules do not exert any force on each other except during collision. Molecules always move along a straight line between two collisions and the distance travelled between two successive collisions is called mean free path. Behavior of gases. All gases expand on heating. As far as changes in volume are concerned, the effect of pressure on solids and liquids is negligible. But gases can be compressed easily. They expand in volume even at constant temperature, provided the pressure is allowed to fall. The volume of a gas, therefore, not only depends on the temperature, but also on its pressure. Boyle's law. Boyle's law states that for a fixed mass of a gas, the volume varies inversely with its pressure provided the temperature remains constant. PV is equal to constant, where P is the pressure and V is the volume. It follows that if volume of the gas is reduced to 1/2, its pressure will be doubled. Energy of a gas at a constant temperature has a constant value and it does not increase or decrease with expansion or contraction of the gas so long as its temperature remains constant. A gas which obeys Boyle's law fully is known as perfect gas or an ideal gas. Boyle's law may be stated as, at constant temperature, the density of a gas increases directly with its pressure. P upon rho is equal to constant. Charles' law. Charles' law states that the volume of a gas changes by gamma P of its volume at 0 degree centigrade for each 1 degree centigrade temperature change, provided the pressure remains constant. V is equal to V naught multiplied by 1 plus gamma p theta, where V is the volume at theta degrees Celsius and V naught is the volume at 0 degrees centigrade. The above relation can be written as V is equal to V naught multiplied by 1 plus theta upon 273. According to equation, a graph between volume and temperature is a straight line. An ideal gas obeys this equation throughout the entire range of temperature. Real gases obey the equation only at high temperatures. As the temperature is reduced, it starts deviating from the equation. Kinetic theory of an ideal gas. A gas consists of a large number of identical, tiny, spherical, neutral and perfectly elastic particles called molecules. In a gas, molecules are moving in all possible directions with all possible speeds. The space occupied by the molecules is negligible as compared to the volume of the gas. There is no force of attraction between the molecules. The collision between the molecules and with the walls of the container is perfectly elastic. The duration of collision is negligible compared with the time spent by a molecule between the collisions. Gravity has hardly any effect on the molecular motion as their mass is too small and speed is very high. Pressure of an ideal gas. Gas exerts pressure due to collision of its molecules with the walls of the container. Let us consider an ideal gas having n molecules, each of mass m, contained in a rectangular box of side Lx, Ly, Lz. Kinetic energy per unit volume is given by E is equal to half rho V RMS square. Pressure of the gas is given by P is equal to 2 by 3 of E. Hence, the pressure of a gas is equal to 2/3 of its kinetic energy per unit volume. Kinetic interpretation of temperature. Average kinetic energy of one molecule E is given by E is equal to Em upon N is equal to 3 RT upon 2N is equal to 3 kT by 2, where K is Boltzmann's constant. So, the average kinetic energy of a molecule does not depend on the nature of the gas or mass of the molecule. It means different gases at the same temperature have same total kinetic energy and same average kinetic energy per molecule. It depends only on the absolute temperature of the gas. Temperature can be interpreted as a measure of the average kinetic energy of the molecules of a gas. Example. Let's take an example of kinetic theory of an ideal gas. Using the ideal gas equation, PV is equal to RT. Calculate the value of universal gas constant. Let's see the solution. We have V is equal to 22,400 into 10 to the power minus 6 meter cube. T is equal to 273 Kelvin. PV is equal to RT. P is equal to HDG. Now, we calculate value of R by putting the values. R is equal to PV by T is equal to 2 calorie per mole per Kelvin. If V is equal to 22.4 liters, P is equal to 1 atmosphere, T is equal to 273 Kelvin, R is equal to 0.082 atom liter per mole per Kelvin. Hence, the value of universal gas constant is 0.082 atom liter per mole per Kelvin. Maxwell distribution function. In a given mass of gas, the velocities of all molecules are not the same, even when bulk parameters like pressure, volume, and temperature are fixed. Collisions change the direction and the speed of molecules. However, in a state of equilibrium, the distribution of speed is constant. Distributions are very important and useful when dealing with system containing large number of objects. The molecular speed distribution gives the number of molecules between the speeds v and v plus dv. The fraction of the molecules with speeds v and v plus dv is equal to the area of the strip. Law of equipartition of energy. Law of equipartition of energy states that for any dynamic system in thermal equilibrium, the total energy gets distributed equally amongst all the degrees of freedom and the energy associated with each molecule per degree of freedom is half kT, where K is equal to Boltzmann's constant, T is equal to absolute temperature of the system. Degree of freedom of a system. It is defined as the number of independent coordinates which are required to explain the position or configuration of the system. The number of degrees of freedom of a system is given by F is equal to 3n minus A, where F is equal to number of degrees of freedom, N is equal to number of atoms in one molecules, A is equal to number of independent relations between the atoms of one molecule. Law of equipartition of energy can also be stated as the total average kinetic energy of a molecule of a given gas at a constant pressure and temperature is equally distributed among all its degree of freedom, and the average kinetic energy per molecule per degree of freedom is half kT, where T is equal to temperature of gas. Specific heat capacity. Specific heat capacity is defined as the ratio of the specific heat of a gas at constant pressure to the specific heat of a gas at constant volume. Its value represents the atomicity of gas. Monoatomic gases. Consider 1 mole of an ideal monoatomic gas at a temperature T and pressure P. The number of degrees of freedom of a monoatomic gas is 3. According to the law of equipartition of energy, average kinetic energy per molecule per degree of freedom is equal to half kT. Average kinetic energy of 1 mole of gas is equal to kT into N, where N is equal to Avogadro's number. Thus, U is equal to 3 by 2 RT, where U is the kinetic energy of 1 mole of gas. Du by dt is equal to CV. CV is equal to 3 by 2 R, but Cp is equal to Cv plus R. We get Cp is equal to 5 by 2 R. Hence, Cp by Cv is equal to 5 by 3. Diatomic gases. The number of degrees of freedom of a diatomic gas is 5. Cp by Cv is equal to 9 by 7. Polyatomic gases. It has 3 transitional and 3 rotational degrees of freedom. Cp by Cv is equal to 4 plus F upon 3 plus F. Cp minus Cv is equal to R is true for any ideal gas, whether monoatomic, diatomic or polyatomic. Mean free path. The molecules of a gas are in a state of continuous, rapid and random motion. They undergo perfectly elastic collisions against one another. The molecules exert no force on one another except during collisions. Therefore, the free path travelled between two successive collisions will be a straight line with constant velocity. The path of a single gas molecule comprises of a series of short zigzag paths of different lengths. These paths are known as free paths and their mean is called mean free path. Lambda is equal to kT upon root 2 pi sigma square p, where sigma is equal to diameter of the molecule, p is equal to pressure of the gas, T is equal to temperature of the gas, K is equal to Boltzmann's constant. Brownian motion. Brownian motion is the continuous zigzag random motion of particles of microscopic size suspended in water or air or some other fluid. This phenomenon was discovered by Robert Brown and is explained on the basis of kinetic theory. Brownian motion increases when size of suspended particle is smaller, temperature of medium is raised, viscosity of medium is smaller, density of medium is smaller. Assessment. Before proceeding further, let us know how much have you learned. Drag and drop the correct option. Did you know? Before the development of modern thermodynamics, it was thought that heat was a fluid and so-called caloric. Bodies were capable of holding a certain amount of this fluid. Hence, we term heat capacity, named and first investigated by Joseph Black in the 1750s. Each molecule exerts a force of attraction on its neighboring molecule, which is called the intermolecular force. The concept of mean free path was introduced in 1858 paper on the mean length of the paths described by the separate molecules of gaseous bodies on the occurrence of the molecular motion by German physicist Rudolf Clausius. Summary. Let us summarize what we have learned. Kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms or molecules. The volume of a gas not only depends on the temperature but also on its pressure. Boyle's law states that for a fixed mass of a gas, the volume varies inversely with its pressure provided the temperature remains constant. Charles' law states that the volume of a gas changes by gamma p of its volume at 0 degrees centigrade for each 1 degree centigrade temperature change, provided the pressure remains constant. The pressure of a gas is equal to 2/3 of its kinetic energy per unit volume. The average kinetic energy of a molecule does not depend on the nature of the gas or mass of the molecule. It depends only on the absolute temperature of the gas. Brownian motion is the continuous, zigzag random motion of particles of microscopic size suspended in water or air or some other fluid. Specific heat capacity is the ratio of the specific heat of a gas at constant pressure to the specific heat of gas at constant volume.